the notes for AP Calculus on the topic of polar functions with the graphing calculator. So here's our formulas we're going to be using again, the same ones we used without calculator. Let's see how we use our graphing calculator to help us solve different problems here. Alright, so let's first look at one of these, sometimes these are called like flower graphs with these polar coordinates. They create these nice, beautiful flower type of graphs here. And it says, here's the graph shown in our figure. And it says find the area of the region that's enclosed by the curve. Notice we're not given an interval where this might apply. It might be 0 to 2 pi, it might be something else we don't know. So the key is with these flower graphs, you can see we've got 3 petals on this one. Each of them have the same area, so we really just need to find one of them. So we can just find basically 3 times the area of one petal. And that'll give us the area, entire area enclosed by the curve right there. So to figure out where the area of one petal, we need to know where one petal starts and stops. And notice where they start and stop on these type of graphs is right at the origin. And remember, for the polar graphs, the one thing you know for sure is true at the origin is that r has to equal 0, the radius, because it's not going anywhere from the origin. That's where all the points start with polar coordinates. So we can just substitute in r equals 0 right here, and then solve that. This part you usually will be able to solve by hand. If for some reason you can't, though, you could use your graphing calculator in regular function mode, which we'll see later in the notes how to go about that. But here you can see you can just divide by 4, and we're really looking for where sine of 3 theta is equal to 0. So let's first figure out where sine is 0. And since we're not given a specific interval, there's a bunch of different places where sine is equal to 0. But let's find the first 2, because we want just one of these petals. So the first place sine is 0 is right here at theta equals 0. Or in this case, we'll just write 0 here. And then the other place, the next place is at pi, then at 2 pi, and so on. Let's just start with the first 2 though. And remember, we've got 3 theta in here instead of just theta. So that's why I erased this theta equals pi, because it's really not theta that has to equal pi, it's 3 theta could equal pi, or 3 theta could equal, 3 theta could equal 0, or 3 theta could equal pi. And then if you divide by 3 to solve for theta, you can see here we get theta equals 0 still, and theta equals pi over 3. So those are the first 2 places that make the radius 0. Here. So that tells us that's going to give us one of these petals. It doesn't matter which of the 3 it gives us. Because these are both in the first quadrant, it's likely giving us this first one here, in the first quadrant here. But it really doesn't matter which one it's giving you, as long as we just get one of them. So be 3 times, and then the formula for area, remember for polar coordinates, we've got the 1/2 out in front, and then it's from the integral from a to b of the radius squared. So we just figured out the lower and upper limits here. We got the 1/2 out in front first. And then we figured out the lower and upper limits were 0 to pi over 3. And then here's our radius right here. So it'd be 4 sine of 3 theta. And then it gets squared times d theta. You can see the next time, if we kept going here, the next time sine of 0 is at 2 pi, so if we said 3 theta equal to 2 pi, and we got 2 pi over 3, that's the other one, then we can go from pi over 3 to 2 pi over 3, that'll give us our next petal, and so on. But we really just need one of the petals. So here's where we can enter this in our calculator. And you can do it in regular mode if you want, just using x instead of theta, or let's get some practice with polar mode, how that works here. So let's look at the 84 first. So to get it in polar mode, so you can use theta, you hit the mode button, And then instead of function, go down here to one that says POL, that's for polar. And then go a second quit. And then we can enter in 3 times a half, or you can just go 3 times 0.5, and then the integral, so math number 9. And then we haven't entered this in yet, so we can just type it in as open parentheses so we can square it. 4 sine of 3. And now we hit the xt theta n button. Notice since we put it in polar mode, it's going to put theta there, just like it looks here. Close parentheses on the sine. Another close parentheses so we can square it. Comma. Now when you hit this button, theta is our variable. Comma. Lower limit is 0. Comma. Upper limit is pi over 3. And you can see we get 12.566. And that's units squared. If you want to put it, but it's not specific units, so you don't have to write that. Just remind yourself it's area. Or on the Inspire, if you have that one, and you can just go new document. Here you don't even need the graphs here, you can just add the calculator. And if you want, you can even make it 3 times a half is just 3 halves out in front. And then the integral right next to the 9 here, from 0, and you can do the fraction here. Pi is right here, over 3. And then open parentheses, and then remember it was 4 sine of 3 theta. So 4 trig sine of 3, and if you want theta, it's right on the same button as the pi here. There's theta. And then we want to square that, and d theta. See, we get the same answer on the Inspire. All right, let's take a look at the next one here. So this one we've got a few different parts here. So here we've got our polar curve r equals theta times sine theta. This time it does give you the interval, 0 to 2 pi is where it applies. It says find the area enclosed by the inner loop of the curve. So we can see we've got an inner loop right here and an outer loop. Here we want this area, the inner loop. So again, what we know is the loop starts and stops when r is equal to 0. So we can solve it that way. Substituting 0 in for r. This time though, notice we've already got it in factor form, theta times sine theta. So either of these could be 0. So theta could equal 0. Or if we set sine theta equal to 0 and solve that, well, the first place sine is equal to 0. Besides 0, which we already have as a solution right here, is at pi. So the next answer would be theta equals pi. The only question is, does that give us the inner loop here, or is that maybe the outer loop? So to see if these are the right, these starting and stopping angles for the smaller loop, the easiest thing to do is probably substitute in an angle between 0 and pi, like pi over 2. So if we substitute in pi over 2, we'll get r equals pi over 2 times the sine of pi over 2. But that's pi over 2, and then the sine of pi over 2 right here is 1. So that's pi over 2 times 1. Well, that's pi is about approximately 3.14. Divided by 2. So that's going to be approximately 1 point, half of 3 is 5, so it's around 1.6-ish. And then we can see what that corresponds to. Is that the big loop or the little loop? Well, 1.6, pi over 2 is straight up the direction. So we plugged in 1.6, yeah, that's about right there. pi over 2. So that does, in fact, give us the little inner loop like we were looking for. If we'd got an answer somewhere up here, 4 point something, then we would know that 0 to pi actually gives us the bigger loop instead. So now, for the area again, it's 1/2 out in front. Integral, now we know, is from 0 to pi. And then we have the radius, which in this case is theta sine theta. And then that gets squared times d theta. So that'll give us the area of that inner loop. So let's go ahead and work out what that is. So up to the 84 again, it's already in polar mode. So I can just put 0.5 and then math number 9, function integrate, and open parentheses, theta times sine of theta, close parentheses, squared, comma, theta is our variable, comma, 0 is the lower limit, comma, pi is the upper limit. And we can see we get 2.191. Again, if you want, you can put units squared to remind yourself it's area, but we don't have specific units, so you don't have to. And again, on the inspire, you just enter in 1/2 or 0.5 either way. The integral from 0 to pi, and then open parentheses so we can square the whole thing. And remember, our radius was theta times sine theta. So you can get theta right here on the pi button. Now be careful on the inspire here. If you just put sine right next to it, oftentimes it won't recognize you want to multiply. It will think it's some other function. So on the inspire, you do need to put times here before you hit the sign. Unlike the 84, it doesn't always assume things right next to each other are multiplying. It thinks that you're trying to create some other function, theta, sine theta, which it doesn't recognize. It'll give you an error. So theta times sine theta, and then squared, and then d theta. And we get the same answer. All right, let's take a look at part B on this one. Same graph here. And now it says a particle is moving along the curve, so d theta dt is equal to 2 for all times greater than equal to 2. So it's just a constant. What this is really telling you is it's kind of combining polar with parametric, where we usually have time here. So it's telling you the angle is changing at a rate of 2. And we don't have units for time here, but this could be like radians per second, radians per minute, something like that. And it asks you to find the value of, oops, let me fix this here, dr dt, specifically at theta equals 3 pi over 4. So that's what we're looking for, dr dt specifically at that angle. So then we're asked, well, based on how the angle is changing, this is asking us, well, how is the radius changing over time, specifically at this instant, when the angle is 3 pi over 4 radians. So it's helpful to write down what we've got here to see how we're going to figure this out. So we have dr dt, that's what we're looking for, specifically at theta equals 3 pi over 4. Well, we have d theta dt, and notice we have r. So from here, we can get the derivative dr d theta. So if we write down that expression here, dr d theta, and then we've got d theta dt. Notice mathematically, if you took these and multiplied these expressions together, let's see what's going to happen. So if we write down d theta dt times dr d theta, yeah, the thetas are going to cancel out, giving us dr dt, what we want. Okay? So it's just understanding how that's going to work there. And in this case, though, it's dr d theta, specifically at theta equals 3 pi over 4. So you could do this one without calculator by finding the derivative of this and then plugging in 3 pi over 4. That would work. But since we have our calculator and we just want the derivative at a specific value, remember we can use the numerical derivative. Okay? So this is going to be, remember theta dt is just 2, so it will be 2 times dr d theta, specifically at theta equals 3 pi over 4. So I'll just put a little note here for when you look back at your notes here. Use numerical derivative on calculator. And let's review how we do that for both the 84 and the Inspire. So first with the 84, we can just go 2, and then it's math, and then remember it's the one that says n deriv, number 8 here. And then we first put what we're taking the derivative of, and that's dr d theta. Sorry, what we want is the derivative of this one. So that's theta times sine theta, close parentheses on the sign, and then comma, the variable is theta, comma, what we're substituting in is 3 pi over 4. And we get negative 1.9179, which you can round to 8. Negative 1.918. Which in context, the units for dr dt would be like units per second, units per minute, units per hour. We don't know what the units per time here are. So in other words, over time, at this instant, it's showing us the radius r, or the distance from the origin here is, or r is decreasing at this time. We got a negative answer. Put in context here what we just figured out here. And then let's review how we do this on the Inspire. Again, you would just go 2 times, and then menu, calculus, derivative at a point. The variable in this case is theta. Again, you could put x here and just put everything where there's a theta, use an x instead, that would be fine. We want to substitute in 3 pi over 4 is the value. We want the first derivative. And then you just have to type in your function, which is theta sine theta. Again, make sure you put times, so it knows you're really trying to multiply those. And enter, and we get the same value there. All right, let's take a look at one more part on this problem here. This one says from pi to 2 pi. Notice that's different than our area one from part A, which was, remember the little loop was 0 to pi? So this is saying from pi to 2 pi, and since this is just from 0 to 2 pi, we can see, okay, well, that would represent the big loop, the outer loop there. And that makes sense based on the question. It says find the greatest distance from any point on the graph r to the origin, which is just, okay. So the distance from any point on the graph r to the origin, and we want the greatest is just another way of saying the absolute max. Distance, though, one thing you have to keep in mind is sometimes, remember, r can be negative on these. So distance actually could be r, but really the absolute value of r. And since we don't know if the greatest one is, for the absolute value, it could be the largest positive number or the smallest negative number. Okay? We have to find, based in order to find the greatest distance, we have to look at both the absolute max and absolute min, whenever it's the absolute value like that. All right. So what we want to do first, since we're trying to maximize r, is take its derivative. And notice, because it's theta times sine theta, you have to use the product rule. Here we actually have to do this part by hand, because unlike the other one, we don't just need it at one specific value. We need the whole expression for the derivative. So here the derivative we'd write as dr d theta. Using the product rule, derivative of theta, just like the derivative of x, is just 1, times the second one, sine theta as it is, plus the first one as it is, theta, times the derivative of the second one, derivative of sine is cosine. So that's our derivative. And we want to see where this is 0 or undefined to find our critical numbers. But notice sine and cosine, there's no denominator, those are defined everywhere, so we just want to see what makes it 0. So I want to see what makes this equal to 0. The derivative of sine theta plus theta cosine theta. And this one, notice, because we've got two different trig functions and a theta, this would be tough to solve by hand, so we're going to use our graphing calculator. But the key is, whenever you're solving equations with the graphing calculator, we need to use regular function mode. It won't do it, as far as I know, in polar mode on either calculator. Solving equations, you have to go back to the regular function mode. All right, so let's do that for both of these. Let's start with the TI-84. So let's change the mode back to regular. If we had entered any functions into y equals with polar coordinates, we could, they would still stay in there. But here we didn't here, so just go back to regular function mode here. And then y equals, let's enter this in. Sine, everywhere there's theta, we're just going to put x instead, so it's the same equation, just a different variable. Sine of x plus x cosine of x. And then notice, before we graph this, the window size here, it's telling us we're just looking on this interval. So make sure your minimum on the window size, your x minimum, is pi, and your x maximum on the window size is 2 pi. Otherwise, we're going to see more than what we really need to look at. So x minimum, let's make that pi. X maximum 2 pi. Just converting to a decimal there once you put it in. Y min and max, we just have to make sure zero's in between there. So to kind of zoom in a little more, I'll just make it -5 to 5. And then graph it. So this is what we're going to use to draw a number. You can see it starts off negative, hits 0 right there, and then becomes positive the rest of the way. So let me draw a number line here. In this case, we're just looking from, not the whole interval, just from the x min to x max, so from pi to 2 pi, dr d theta, our derivative. You can see it starts off being negative until some value a here, where it's 0, and then it's positive the rest of the way. Again, just looking at, on our graphing calculator, the y values. So what this shows us is the radius would be decreasing and then increasing. So it looks something like this. So if we were just looking for, if we didn't have the absolute value, the minimum would have to be here at a, and the maximum would have to be either pi or 2 pi. But the absolute value means we have to look at all three of these. But let's first figure out what a equals, using our calculator with the zeros. And we'll store it once we do that. So second calc 0. Lower bound to the left of A, enter. Upper bound to the right of it. Enter and guess in between there. So A is equal to 4.913. So let's write that down on paper. And let's store it in our calculator. And then we'll look at how we do the same thing on the Inspire. Second quit, store alpha A. All right, then for the Inspire, I'm going to close this one out here and open a new document. Okay. And then add the graphs first. So then we go back, we want a graph here is the derivative, sine of x, or in this case we have to enter in as x in regular function mode, plus x cosine of x. So sine of x, in regular function mode you have to use the variable x there, plus x, and here's another place, don't just hit cosine. It's going to try to create this weird thing, give you an error. Make sure you actually put times, otherwise the calculator is not going to understand on the Inspire that you actually want to multiply them together. Times cosine of x. And enter. And again, notice if we try to do our number line here, that's way more than we need here. So menu, window settings. Again, the lower limit, the x minimum, remember, was pi. And the x maximum was 2 pi. And we can leave these -6 to 6, that's fine. There we go, we get the same number line. And then to find the 0, you go menu, analyze graph, 0, lower bound, click to the left of it, upper bound right of it, there it is. We already wrote it down with the other calculator, but store it on this one too. Store as A. All right, now let's go back to what we need to figure out here. Since it's the distance, and distance is the absolute value of R, we have to look at both the maximums and the minimum. All three of them to compare. After we put the absolute value around it, which one of those is going to be the largest for this distance away. So all we have to do now is find each of those. So let's say we start with pi, so we can say we want to find the absolute value of R for each of these. Want to compare? So the first one is pi, so that would be absolute value of pi times sine of pi. See what that equals. The next one we stored it as A, so this would be absolute value of A times sine of A. Oops. Sine of A. And then find the absolute value of the other endpoint was 2 pi, so 2 pi sine of 2 pi. Now you could use your calculator for all of these. But sine of pi is 0, so that's going to make this whole thing 0. Absolute value is going to keep it 0. And sine of 2 pi is also 0. So both of those end up being 0. And that's about as small as the distance can be, right? So it's the maximums, but remember this one has the absolute value, so we have to check the minimum as well. And so this on your calculator, how we can calculate it, here we just use the absolute value signs, you hit the math, and then go over to hit the round num, it's the first one, ABS for absolute value. And then we stored it as A, so we go alpha A, and then sine of alpha A. And then close parentheses on the sine and the absolute value. And we get 4.814. And notice that's larger than both of the zeros, so that's our maximum distance. And you can see why we needed to consider it, because look at what happens if I just go second entry. If I delete that absolute value function here and just found this, a sine of a, notice it's actually negative. So that's why it was considered the minimum if we didn't have the absolute value of just r. And that's why we had to consider it when we're looking for the greatest distance, because in this case, that was the largest distance away, even though r was negative, because the absolute value just makes it positive. That's how far away it is, 1.814. Right. And then let's see how we do this on the Inspire. Again, Inspire, you just need to calculate this, so you just go dock, insert, calculator. And again, the absolute value on the Inspire is again on the same button we use all the time next to the 9 here. There's the absolute value sign, just looks just like it. And then we can just restore it as a. So a, and again, probably need to put times, and then sine of a. Get the same value with the absolute value. So let's write our answer and then justify it. So we can say the greatest, I'm just changing this question into a statement here. Distance from any point on the graph to the origin is 4.814. You can put units here, we don't have to because it's just general units. And since we're justifying it, it's probably a good idea to reference the time. So you can say, even though it didn't ask for it, or the angle I should say, not the time, at theta equals a. And then to justify it, similar to how we justify other absolute mins or maxes, since, well, the one that was greatest was this one, right? So you could say since the absolute value of a sine of a that was greater than the absolute value. Now here they're both 0. If there are different values, you could put them in order. But here it doesn't matter which one you put first here because they're the same anyway. Pi sine of pi. And here it's not greater than, it's just equal to the absolute value, because they're both 0 in this case. 2 pi sine of 2 pi. Let's see how we justify.